absolute value of x times y is less than or equal to 2 or greater. It doesn't really. Right? The work is the same if it's greater than or less than. All right, for this particular problem, when you put down your quadrants, here it's always easy. It's plus. So the x's and y's are positive. So your formula ends up to be x times y is less or equal to 2. And since everything's positive, you get y is less or equal to 2 over x. So it's the hyperbola. These are the y's that are less than. So that's pretty rinky-dink. But if you go to this quadrant, your x's are less than 0 and your y's are bigger than 0. So absolute value of x is equal to negative x. And then you get, so you're going to get negative xy is less or equal to 2. However, when you multiply, let's say you hit both sides with a negative, so you're going to get x is bigger or equal to negative 2 over, let's do that, 2 over x, like this. When I multiply by negative, it flips the sign, but the x is negative 2. And so when you divide by the x, this sign flips around one more time. And that's why it actually doesn't do anything to the symbol. So so one negative is when you're multiplying by this negative through. So that's going to switch the sign. But when you divide both sides by x, that's also negative. And so when you multiply both sides by a negative, this inequality sign switches around. So you're going to get here that your y's are less or equal to negative 2 over x, and your formula looks, your plot looks like this. I was bringing back good memories, right, with hyperbolas. So there you go. So it's going to be this area under here. The y's are smaller than this hyperbola. That's why you get what you get. For those of you traveling, you didn't get to go home for Thanksgiving? I binged all of Ragnarok. And I started on Ted Lasso. I never watched any TV.
Ted Lasso.
That was hilarious.
I love Ted Lasso. That's a top 5 show.
It is.
We get motivated.
I used to bring in, because there was a period here where people would bring in videos to start off their class. Like, I'm going to bring irrelevant videos, and we do impractical joker bits.
Oh,
my favorite one's the bingo one. All right, so that should make sense now. So if you got a revision on this particular one, that's what's going on. And I think this was the only one where you had something weird like this. But keep aware of that. If you're multiplying both sides by a negative number, that it also switches around the sign. Make sense? There's something else I was supposed to actually ask. Find you guys out. Can't remember right now, but I think this was it for at least getting this done. Are there any questions? All right, for your open problem project, like it is an open problem. There's a lot of mathematicians working on these open problems. Some of them are taking it as PhD theses. It's not a good idea to do that because it's like they talked about at Andrew Wiles. Oh, I do remember this. On the back of the Andrew Wiles thing, there were 2 questions. The first one was, how do you think the math community felt about Andrew Wiles keeping things secret? The reality is we don't disseminate what we do via publications. It's impossible. It took, I think, a total of 3 years for one of my pure math papers to get into publication. And then journals are pretty they're not like the med journals where they have a big staff putting things together. You LaTeX it up, you send it in, someone reviews it, but it takes a while for it to actually come into print. They're only starting now with online journals. I think that the math community is probably pretty slow about that. I told you Neil Calkin was the first to make an electronic journal that was purely online. So this is kind of a new thing. And even at the Math Association of America, you're going to the JMM, like you'll see that there's a resistance to change, which is, it's just not there. Like they were asking me, what do I think about mathematicians saying data science is not math? I'm like, no one's waiting for you. the train will leave. Like that's like, no one's waiting for you to decide that. But they also didn't want to have an online journal. There was a resistant group that doesn't want it. And so, you know, Colonel Clark and I are both on the editorial board and we're like, make it online. The people that won't want to read this are not the people who will care if it's online or not. So drop that. So it's that kind of little resistant on it. But the way we still disseminate information is just by talking to each other. Typically, you don't steal ideas in mathematics. It's you saw Barry Mazur at the end of the documentary talking about all the people that were involved in the Fermat's theorem, and there was not a hint of jealousy in him. He was completely like, look at all these cool things these mathematicians did. So that it's like it's a low stakes discipline, and people give credit to whoever did whatever they did. So to not talk about your research for that long and to hide it, it's like goes against our culture. So I don't know if you picked that up, but it was like people didn't seem to, their facial expressions weren't like he was keeping the secret, and that's not cool. That's what they look like to me. I would know that they, you know, my stuff that I've done, people knew about it long before it ever came out to publication. So to wait till publication or wait and disseminate that as one talk is just not cool. And it's we went to see him actually at Princeton, and they didn't bring him out. We actually just saw like Peter Sarnak and the math forum. We went down to Princeton and we met some of the people in the video. And we can do that in the spring, and I give the people running the math forum a heart attack. But if you guys want to do that, I can send out an email. We can organize that. It's worth it to just meet some of these people.
Why didn't they bring him?
I don't think he's very, very well liked.
Wow.
He didn't get the Fields Medal. So the Fields Medal is our version of a Nobel Prize in math. And he was young enough to get it. He did not get the Fields Medal.
Because he like worked on it on his own.
I don't know if that's the reason, but you know, if you have, it's the same here, right? If you have a cadet who's really, really like performing well, great at academics, if they're not great to have on the team, people dislike them. They don't want them on the team. It doesn't matter how well they do. All right, so let's go to more interesting things, maybe? I don't know. So I'm kind of going through the typical kind of book that they have. For a foundations type course. And it's really methods. It's kind of like discrete math, where you have method after method after method of proofs. This is not a methods class. This is like, I don't know, you learn how to write proofs. You kind of have to just write proofs. So one of the things that they show you is they show you how to show something's unique. And I'd like to have that organically come up where we show something's unique without having a method behind it. It's like, this is kind of the technique that we use. So we're talking about supremums and infimums. They don't necessarily have to be in the set. They're not the same as a max and a min. Max has to be in the set, min has to be in the set. Not everything that you have as a set is going to have a max and a min. And you have some examples like that. But it always will have a SUP, and it always will have an inf if it's bounded. How do we know, though, that the SUP is unique, that there's only one SUP? Can you make some bizarre set up where that you have two different SUPs? The answer is no. It's unique. So here's how you do it. Suppose I have S is bounded above. And suppose S1 and S2 are both SUP of S. So you have two SUPs. Did you do this where you prove things are unique in discrete math? You might have in abstract. So the trick is to prove something's unique is really hard. How do you prove there's only one? So what you do is you assume there's two and you show they're equal. It's been a while, right? SUP is the upper bound. That's the first property of SUP, that you have the SUP as an upper bound. Put a little addendum here. The property 1 of SUP. So far, so good. And property 2 says that if there's another upper bound, it's got to be the best upper bound. So I'm going to apply property 2. Sure. Good. Because they're both SUPs, if there is another upper bound, your upper bound has to be the smallest one for both of them. They're both SUPs. I'm going to label this 1 and label this 2. Just high school algebra, not high school anymore. 5th grade, 6th grade. I don't know where you learn this. Linear inequalities. You can subtract from 1 the S2 from both sides. So yeah, S1 minus S2 is less or equal to 0. And 2 says that S2 minus S1 is less or equal to 0. But I can multiply 2. So how did I do this? Okay, you can multiply number 2 by -1. I get S1 minus S2 is bigger equals 0. So what I have now is that I have 0 is less or equal to S1 minus S2, which is less or equal to 0. What does that mean, Sam?
That S1 has to equal S2.
Why? One step back.
Because the stuff in the middle has to be 0.
Right. Boom, done. That's how you prove something's unique. Assume there's 2, show they're equal. Did you guys have that in discrete? Zoe? You use this a lot for real analysis. Like you have a limit, show that it's unique. Or you have a limit and you have to show that it is something, then you use the uniqueness of the limit to say, well, it's got to be this one thing. So you use this a lot. All right, I'm going to show you an alternate definition for SUP and INF both. And then we're going to do some boards. So, this definition looks unpleasant, but you use it a lot in combination with sequences converging. So if you're taking real analysis, you'll be epsilon to death. And when you see epsilons in two different definitions, you can connect the two. So sometimes it's useful to use this definition of SUP and INF. So an upper bound U of a non-empty subset S in R is SUP S. This little symbol means if and only if. That means it's like a definition. It's true in both directions. So we say for every epsilon bigger than 0, there exists an S epsilon in S such that U minus epsilon is less than S epsilon. And this is really hard to understand, but what it means is if I take the SUP and I drop the SUP by just a little bit, usually epsilon is 0, but small, it's like small numbers. So you drop that SUP by just a little bit, then there's going to be sequence members or set members that are going to be above that SUP. The SUP was the best bound. If I lowered it just a tiny bit, there's going to be stuff in the set that was bigger than that. So I can't drop it and I let it be an upper bound anymore. So a few years ago, I think it was 5 years ago, I taught foundations. I gave them this definition. I explained it just like I explained to you guys. And then I gave them proofs to do because I think we did real analysis a little bit earlier. And they just didn't understand it. So I came back and made some visuals so they could see it. So thank them. All right, I just took the sequence n divided by n plus 1. And I plotted it so you could see it. So this one right here is the plot of n divided by n plus 1. We already know that's going to converge to 1. The SUP is going to be 1. So what I did here is I took different values of epsilon and then I dropped the SUP, which I know to be 1, down by a little epsilon. So if a SUP is 1 and I drop by 0.1, I get 0.9. So that's this gray bar right here. I've just dropped this gray bar just a little bit. And if I drop that gray bar just a little bit, there's going to be like, I think SUP minus epsilon is 0.9. I can actually go down here to 0.9. Right there. And I can actually see that after these guys right here are all going to be above that 0.9. Right, I can actually see the numbers. If I drop it by 0.01, I will have 0.99. I can actually go down here and see, here's my 0.99, and here's the guys that are going to be now above that 0.99. So that's my S epsilon right here. I can just take the first one that went above 0.99. Does that make sense? There's going to be actual set members that are going to be bigger when I drop down this little line. Like you dropped it down too far. Make sure you understand, because I'm going to send you boards and actually find these things yourself. You can use Excel to find them, just like I did. Questions?
Are you looking for like a certain, when you drop, can you drop it to 0.98969?
You could drop it. Epsilon is any real number that's bigger than 0. So I could, the alternative definition says if I drop that even a smidgen, there's going to be stuff above it. in the set. Like that's another way of saying this is the best bound. Because if I drop that bound just a tiny bit, it's no longer going to be an upper bound. There's gonna be stuff above it. Make sense? I did another one here and I can't remember what I was trying to visualize for it. Yeah, I don't know why I did this. I just think I wanted to play around with it. I gave some of you a example on your feedback from your sheets, taking something like -1 to the n divided by n+1. So then it oscillates. It's bounded. Just because something's bounded doesn't mean it has to converge. So there you have a sup and an inf that oscillate. So you still have a sup and an inf, and this stuff still works. If I take the sup and drop it down a little bit, there's going to be sequence members that are above it. All right. I gave you sheets last day before we left. Some of you don't have it. I mean, I think I've purged everything. So look up someone else's sheet. And if you weren't here in class, Lalata, you're still responsible for the first part. I can't remember. Was it does anybody have their sheet with them?
Yeah.
What was the first question on it?
Is S bounded in R according to the definition?
Yeah, okay, so these things have to be, I recorded class, so. No, actually, yeah, I did. Yeah, I recorded it. I'm gonna leave this up so you can see it.